Yes, sir.
Welcome everyone today evening or perhaps afternoon or morning in different time zones to this ICTS distinguished lecture by Professor Joel Lebowitz. We are very grateful that Professor Lebowitz could give this lecture virtually. We have been actually suspended in our special lecture series in view of the lockdown, but Professor Lebowitz was, of course, an exception when someone of his stature is ready to give a lecture even remotely. We were very happy to to go ahead with this. So in some sense, we have restarted the ICTS distinguished lecture, and Professor Lebowitz is also no stranger to ICTS. He has collaborated with some of our faculty and has visited ICTS and gave a very nice public lecture on entropy and the arrow of time, I think about 4 to 5 years ago, if I'm not mistaken. So the ICTS Distinguished Lectures are one of our very special lecture series. They are standalone lectures given by some of the most distinguished scientists, contemporary scientists and mathematicians across various disciplines. As you might have seen from the webpage of the Distinguished Lecture series, it has been, there are a number of luminaries who have given these lectures, including people like Duncan Haldane, David Gross, and several others. And so it's a long list, and I won't go through all the names, but so it's a special privilege and pleasure to welcome Professor Lebowitz for this lecture in this series. And we hope, as we were just talking, we hope visit us sometime as we open our programs to the in-person mode. But I guess one upside of the current Zoom lecture is that I see nearly 200 participants joining in, and I'm sure from many parts of the world. And this is something that wouldn't have easily happened in the other format. So there are some advantages. So with that, I will hand it over to Professor Abhishek Dhar, who will introduce the speaker. So go ahead, Abhishek.
Thanks a lot, Rajesh. So I'll give a short introduction. So it's a great pleasure and indeed a great privilege to introduce Professor Joel Lebowitz, who will give today's lecture on statistical mechanical ensembles and typical behavior of macroscopic systems. So Joel Lebowitz is George William Hill Professor of Mathematics and Physics at Rutgers University. He's a distinguished mathematical physicist, widely acknowledged for his outstanding contributions in nearly all areas of statistical physics over a period of more than 50 years. Some of his most important contributions include rigorous results on the Ising model, including his derivation of the so-called Lebowitz inequalities, work on the existence of the thermodynamic limit for Coulombic systems, rigorous results on equilibrium properties of hard sphere systems and the convergence of the virial expansion, developing important dynamical models such as the Katz-Lebowitz-Spohn or KLS model, and algorithms such as the Botz-Kalos-Lebowitz or BKL algorithm, exact results on large deviations and fluctuation relations in non-equilibrium systems, and developing a rigorous framework for the study of non-equilibrium steady state in heat transport. Joel has been deeply involved in explaining Boltzmann's vision, and in particular the emergence of irreversibility and time's arrow. Joel is honorary editor of the Journal of Statistical Physics, which he founded in 1969. And he was also the editor of the famous Dom-Lebowitz series on phase transitions and critical phenomena. This constitutes two very important resources of articles for the statistical physics community. Joel has been organizing the famous Rutgers Statistical Mechanics Conference since 1959. And this is quite an amazing meeting that has been running now for more than 60 years and 120 meetings without almost any break. I don't know, during the pandemic, maybe there was a break, I'm not sure. Joel Lebowitz is also actively involved in human rights issue and is the co-chair of the Committee of Concerned Scientists. This committee has succeeded in restoring the basic human rights of a number of scientists in various parts of the world. Joel has been awarded numerous honors, including the Boltzmann Medal in 1992, which is the highest prize in statistical physics. Yeah, I won't name all the other numerous prizes that he has received. Joel has been an inspiration and sort of a reservoir of ideas for generations of physicists, and is often referred to as the soul of statistical physics. Today's talk by Joel will address one of the most basic questions. Why does statistical physics work? Unfortunately, most textbooks on statistical physics do not actually provide a clear discussion on this issue. And students and also people who are teaching are usually left wondering whether ideas such as that of ergodicity are or are not relevant, and whether or not quantum mechanics plays a crucial role in the discussion. One of the key concepts, that of typicality, is rarely mentioned or emphasized. And so these are the things that Joel will explain in today's talk. With that, I welcome Joel to deliver the lecture.
Thank you very much, Abhishek. It's really a pleasure to be again in spirit, at least in Bangalore, and welcome to all participants. So let me begin. I hope you can see my slides. So the title of my talk is Statistical Mechanics and Mechanical Ensembles and Typical Behavior of Macroscopic Systems. The abstract reads, in this talk, I will focus on describing in a qualitative way the reasons why statistical mechanics is able to predict with great certainty behavior of macroscopic systems, both in equilibrium and out of it. I will relate this to the fact behavior is typical for systems represented by the usual Gibbs ensembles or those derived from them. I think when I say the usual Gibbs ensemble, I mean basically the microcanonical ensemble for a isolated system with a given energy. This microcanonical ensemble takes small phase space volume to indicate small probability. And I will assume this and not try to justify it. So let me begin then. It says the word typical is used in ordinary language to denote a state or behavior usually observed in a given situation. So an example, I say glasses at room temperature are typically hard. I chose this example because I can bring in here the qualification at room temperature. At high temperature, glasses are typically not hard. They melt and they soften. To make this more precise, what do we mean by being typical? We have to specify some probability distribution P over some space omega of elements X, and then say that an event or behavior is typical if it has probability close to 1 with respect to this probability P. So for the context for the talk now, the probability measure is going to be the microcanonical ensemble, and the elements X will correspond to microstates to the of the system in the classical case, and the quantum case I'll discuss later. And saying for macroscopic systems, an overwhelming majority of the microstates in the microcanonical ensemble gives the same thermodynamic behavior. And I'll try to explain this more. Therefore, such behavior is typical. In fact, the fraction of systems with noticeable macroscopic deviations from the average behavior computed in such an ensemble is exponentially small in the number of degrees of freedom of the system. The functions on the phase space which correspond to such thermodynamic behavior will be described later. Say analogous statements, namely that you have a majority of a certain set have a certain property, or a certain property is typical of that probability distribution, will hold for exponentially small subsets of the microcanonical ensemble, which will describe systems in non-equilibrium macrostates. Now again defined below, with respect to the microcanonical measure restricted to such subset. Think of the microcanonical measure as a uniform over the energy surface or some thin shell of it. In particular, this will apply to subsets of the energy surface or energy shell, in which the typical behavior is a time asymmetric approach to equilibrium, encoded in the second law unobserved in individual macroscopic systems. Once one accepts applicability of these measures or ensembles to physical systems, which is what I said is going to be a basic assumption, which I shall not try to justify here, they can be used to predict the typical behavior of individual macroscopic systems and not just some average behavior. And this is what's very important when we talk about macroscopic systems. So observed behavior does not require explanations based on ergodicity, time averaging, or subjective information theory. So this is what I will try to convey in the remainder of this lecture. I'll begin with classical systems where statistical mechanics was first developed by Boltzmann, Maxwell, Gibbs. It's in fact, the macroscopic behavior I'll consider here is pretty much the same for classical as quantum systems. No, so I'll start then with classical systems. In classical systems, sorry, so I have to start. In classical,
sorry, can I just make one announcement? I mean, so I'll just make one announcement. So if you have questions, so for the participants, if you have questions, please put them in the chat box. Maybe we'll stop at around 40 minutes or at some point in the middle of the talk, we'll stop once and Joel will answer if there are not too many questions, he will take all the questions, or at least we'll try to take up as many questions as possible. So please put your questions in the chat box. Thanks, Joel.
Thank you, Abhishek. So can you see the slides and can you see me?
Yes.
Okay, good. In classical mechanics, the microstate of a system of n particles confined to a region V in d-dimensional space, which again will be usually 3 dimensions, is a point X in the 2dn dimensional phase space. N is the number of particles, d is the dimension of the space. You have 3 degrees of freedom for position and 3 degrees freedom for velocity. So altogether, the phase space has 2dn. If d is 3, 6 n dimensional, and x is given the microstate of the system is given by specifying all the positions and all the velocities. I will take here and what follows always is that the mass of the particles is equal to 1 in one positive thing. So there won't be any distinction between velocity and momentum. And the time evolution will be given by a Hamiltonian, which conserves energy. So if you look at the value of the microstate of the system at time t, this will be given, if you start with a microstate x at time 0, you will have an evolution operator, t sub t, which tells you how this microstate or phase point x evolves in time. And it will be confined to the energy surface hx equals c. Now, for a macroscopic system with large n, say n, say bigger than 10 to the 20, for such a system, it is more appropriate to replace the energy surface by a thin shell surrounding that surface. I refer to it as gamma E. You can think of the shell as being as thin as you wish. Just it's first, always when we talk about macroscopic systems, the quantities are not absolutely precise, but mostly I use an energy shell instead of an energy surface, not to have to bother of defining surface area on the energy shells, but you can think of it as an actually energy surface. And I will take also just to begin with that I don't have conserved quantities like the linear or angular momentum, so that's only a priori conserved quantity is the energy. And so the kind of Hamiltonian I have in mind here is the usual one, namely you have a sum of a kinetic energy term, and you have the sum of pair potentials, and you are in a cubical box, let's say, with reflecting boundary conditions, so that there is no linear momentum, is not a conserved quantity. And the Rij are just the distance between the particles, and the time evolution is given by the Hamiltonian equations of motions. Time derivative of the position is just the velocity. Time derivative of the velocity is given by the force acting on the particle due to all the other particles. And I say they're at the boundary, they're reflecting boundary conditions. Now, the time evolution, which I mentioned before already, is given by this evolution operator, t sub t, and this is reversible. That's an important point. The sense in which it's reversible is the following. Consider some microstate given by positions in velocities as before. Now consider reversing all the velocities. And then what's true is that if you first evolve the system, for a time s, I don't know, I don't know if you can see it here. If you first evolve the system for a time s, and then reverse all the velocities, and then evolve it again for a time s, you get back to your initial state with all the velocities reversed. So this is a property of the Hamiltonian equation of motion without a magnetic field. If you have a magnetic field, you have to reverse the magnetic field also. But I say I'm going to consider just the simplest case, a system consisting of a single species of particles, all of mass 1, given with a pair potential, which is like a hard core, or Lennard-Jones potential, short-range potential. And they have solution. Okay, so this is given by this. To describe the macroscopic state of such a system of n particles, and I said we are talking about a macroscopic system with n 10 to the 20, maybe 10 to 23 or 10 to the 18. In a box V, we make use of a much cruder description than that provided by the microstate X. We shall denote by M such a macroscopic description, and by MX the macrostate of the system in the microstate X. So the amount of information, of course, in M of X is much smaller than that contained in the microstate X. Now, how exactly do you choose the microstate? Rather, how exactly do you choose the macrostate? The microstate X is here given. It corresponds to specifying all the positions and velocities. Remember, we are talking here classically, where this is a well-defined notion of a system of n particles having a microstate specified by all the positions and velocities. But so the macrostate is somewhat dependent on how precise a macroscopic description we are interested in. In all cases that I will consider, the state M of the macroscopic system will depend only on the values of certain thermodynamic functions. Like these, what I call thermodynamic functions are the ones which are sums of single coordinates of single particle positions and velocities, and maybe of pairs of particles. And these functions are symmetric in interchanging the positions and velocities. You can think of it like this could be the kinetic energy of the system. This could be the kinetic energy of the system. This could be the potential energy. It could be the kinetic energy in a given part of the box, total energy in a given part of the box. Any of those things, you should think of it. So an example of how to define a macrostate is divide the region V, where these particles are, into K cells, where K is large, but still much smaller than the number of particles. So each of the cells is going to contain many, many particles. I mean, you can think of the cells, that's a region like millimeter inside a little box of millimeter, or even smaller than that, but still, if you have 10 to the 20 particles, each of these cells will contain many particles. And you can say define the macrostate by specifying the value of some of the thermodynamic function, representing the number of particles, like saying the total momentum and the amount of energy in each cell and number of particles. This is natural from the thermodynamic point of view because the number of particles, momentum, and energy in each cell are locally conserved quantities. These are the quantities which will change, in fact, slowly in time. And we can, but we can also use more crude definition of macrostates by really just specifying, just dividing up your box into two parts, the left part and right parts, and then saying how many particles, what fraction of particles are in each of the sides. So clearly there are many microstates, continuum, which correspond to the same macrostate. And I will call, this is very important, gamma sub m is the region in the energy shell, gamma E, consisting of all the microstates X corresponding to a given macrostate M, and by absolute value gamma M, the phase space volumes like the Liouville volume, or in the simplest cases, just like the Euclidean volume is this 6 n-dimensional space. So taking h of x to be of the form which we had before, it can be shown, this is Ranford's work, essentially for all reasonable choices of the macrostates, there is in every energy shell a dominant macrostate. And this dominant macrostate contains almost all of the volume of the energy shell, namely the ratio of the volume of this macrostate, the equilibrium macrostate, by definition, divided by the volume of the whole energy shell, is very close to 1. I will not specify how close to 1 it is. Think of it depending on size of the system, depending what you choose, but it's something which is very small. And then a system is then, in the macroscopic, we say, is in thermal equilibrium relative to the choice of the M's if the microstate belongs to this region, gamma M equilibrium. Then the macrostate is a non-equilibrium state. Like if you specify having 60% of the particles on the left half of the box, 40% on the right half side, then the volume of such a macrostate is much, much smaller than the volume of the equilibrium states, which itself is very close to the whole volume of the energy shell. It's essentially a consequence of the law of large numbers over there. And here is just a picture, I think drawn by Radi Timulka, that given the energy surface or energy shell, you have one region which corresponds to equilibrium, which is very large. In fact, this is a much better picture. It takes up almost all the volume over there, but it's still obviously just a schematic picture. It does not take into account any topology or anything like that. Then I think all thermodynamic functions, not just those used to define the macrostates M, have approximately the same value for almost all microstates in gamma equilibrium. In fact, they have the same value for almost all microstates in the energy shell. As we said, because the volume of this region corresponding to equilibrium is very close to the volume of the whole energy shell. And therefore, these values are therefore typical for this uniform measure on gamma M equilibrium, which is really, say, basically, as far as volumes go, the same as the volume of the whole energy shell. I say it is this fact which justifies using the microcanonical ensemble. I mean, when you are told, I guess usually in many classes, that the microcanonical ensemble represents a system in equilibrium, of course, that's not quite true. Phase points, microstates in the microcanonical ensemble can correspond to something wildly non-equilibrium. All the particles being to 1/2 of the box, or the temperature in the box differing very widely. Nevertheless, you are told to compute the equilibrium properties by taking the averages over the microcanonical ensemble. And the reason this works is because almost all the volume of the microcanonical ensemble corresponds really to the region corresponding to M equilibrium. I mean, this is, of course, this is true for large macroscopic systems. When you're dealing with systems, maybe with a few thousand particles or what, it's still true to a very good approximation, but it becomes really precise and very definite when you are dealing with truly macroscopic systems. I'm saying why ergodicity doesn't matter here is that at least ergodicity in the mathematical sense corresponds essentially not only the thermodynamic functions, which we are interested in for the behavior, macroscopic behavior of the system, but all functions, all measurable functions, something like that, being, namely, is that the time average of any of these measurable functions is the same as an ensemble average over the microcanonical ensemble. But we are not really interested in all possible functions. I mean, it doesn't matter, for example, if you take the function which represents the 20th particle distance from the center of mass, if that is, if the energy surface or energy shell is not ergodic with respect to some very special functions. We are interested only in this thermodynamic type of functions. So saying most microstates in the energy shell correspond to the system being in equilibrium. And the same thing is true actually for quantum system, for most wave functions in corresponding energy shell in the Hilbert space. Of course, it's fortunate that there are microstates which correspond to macroscopic systems which are out of equilibrium, or we would not be here. We are certainly not in equilibrium, but we could still be represented in principle by a microstate in a given energy shell. Of course, we're talking, say, idealized situations, isolated systems evolving according to Hamiltonian evolution. So Cassidy knows the time evolution of the macrostate, which depends on the microstate X, which depends on time according to the Hamiltonian equation of motions, when the system starts out at T0 and some macrostate which is not an equilibrium state. Means it starts out in a microstate which is in gamma m, where m is not m equilibrium at some initial time T0. Now, Boltzmann, Maxwell, Kelvin, etc., argued that given the disparity in the sizes of the gamma m corresponding to the various macrostates, with the equilibrium macrostate being by far having the largest volume, if you consider evolution of a typical point at microstate with respect to a uniform measure on the subset, almost it will be such that as it evolves in time, you look at its macrostate or the volume of the macrostate M corresponding to the microstate at time t will not decrease, because you start out in non-equilibrium, which has a very small volume, and as the system goes, unless there is some obstacle, conservation law or something, it will typically go to the larger ones. So the evolution towards equilibrium of macroscopic systems, which starts in the region non-equilibrium macrostate and are kept effectively isolated afterwards, is typical with respect to the microcanonical measure restricted to the region of phase space corresponding to a macrostate. I mean, phase space, I mean, here's the energy shell. And we have assumed, again, as before, remind you, that such measures give the right probabilities for physical systems. In fact, one can argue that the phase points in gamma m, which do not behave typically, namely going towards larger macrostates with larger volume, will be exponentially small as the number of particles. Now, to make the connection with the second law, Boltzmann defines the entropy, we call it the Boltzmann entropy, of a macroscopic system in a microstate X as being the log of the volume of the macrostate M corresponding to that microstate. Imagine that you have divided up your energy shell into something corresponding different macrostates, like the example I gave before, or some other one I'll use later, then takes a volume of that region in the energy shell, take its log. This is going to be this entropy of the macrostate obtained from a given microstate. Now, here again, you see, if you look now for the entropy of the equilibrium macrostate, this will be a log of the volume of the region corresponding to equilibrium, which, as we said before, is just the log of the volume of the whole energy shell. So it's perfectly fine to take the entropy of an equilibrium system and compute it microscopically by taking the log of the volume of the whole energy shell, because this is the leading order in the size of the system, entropy being an extensive quantity, is just the same as taking the log just of the volume corresponding to the equilibrium region. So in Boltzmann showed, in fact, that he could compute such thing for gases, that this agrees with macroscopic definition of the entropy for gases purely macroscopically as done by Clausius. So this was very important contribution of Boltzmann. And I think that Boltzmann's heuristic argument for the non-decrease of entropy based on relative phase space volume, saying that as a system microstate evolves in time, it will be going to regions which have corresponding to macrostates with larger volume and eventually to equilibrium, is indeed, in my opinion, the correct explanation for the behavior of behavior typically observed in actual macroscopic system. If you start the system with a non-uniform density, it will tend to even out, or with a non-uniform energy density or particle density. And this is, but this is not a mathematical theorem. So what could we do about mathematics? And say Marquardt said, Marquardt was a famous probabilist who died, I don't know, maybe 20, 30 years ago. He says an argument convinces a reasonable person, while a proof convinces a stubborn one. So what would a proof consist of in the context we're talking about? It would be provided if you could rigorously derive from the microscopic dynamics kinetic and hydrodynamic equation, like the heat equation, the Navier-Stokes equation, commonly used to describe time asymmetric entropy increasing behavior of macroscopic system out of equilibrium. I say this has been achieved so far only for the Boltzmann equation for dilute gases, and it was done rigorously in a certain limit. Of course, as we see, you have to define limit by Oscar Lanford in 1975. Let's see there. So let me try to say what Lanford's derivation is. So first of all, following Boltzmann, we refine the description of a macrostate M by noting that the microstates X, which is specifying all the positions and velocities, can be considered as a set of endpoints in six-dimensional one-particle space. I think in all texts and statistical mechanics, this space was called M space for molecular space. Dividing up this one particle space into cells delta alpha centered on the position R alpha, V alpha, and these will have volume. The delta alpha we can describe macro, some people would call it mesostates of the system for the microstate in the energy shell, specifying with some leeway always the fraction of particles in each region delta. Before I gave an example of a macrostate by just dividing up the physical space into different regions. Here, dividing up the six-dimensional position and velocity space into different regions. So this is a much finer description. Conversely, supposing I give you some smooth distribution f of xp in the one particle space, which would be a six-dimensional space in general, we define the macrostate m sub f and the corresponding region in the energy shell corresponding to this m sub f by saying that the fraction of particles in this region dx dv of the six-dimensional state is approximately given by the specified function f of xv. Since we are dealing with dilute gas, we can neglect interaction energy. So F actually determines the energy of the macro state, MF. It's just going to be kinetic energy. And then Boltzmann then used his deep physical intuition and hints from Maxwell to derive equations, Boltzmann equation, his name, for the time evolution of the macro state M corresponding to this six-dimensional probability measure F. This says, F is on six dimension. And the reasoning behind Boltzmann analysis, an exact derivation of the Boltzmann equation, is carefully explained in Lanford's beautiful non-technical article. This is, I hope that the slide will be put on the website and you can see the references to it. And I say this is one of the very nicest mathematical physics article, and certainly best article on this subject I have seen. So it's a very strongly considered. So what did Lanford do? Consider a gas consisting of n spheres of diameter d. D is not dimension. We are not exactly in three dimension. And this system evolves according to Hamiltonian dynamics. And since you have hard spheres, you have to specify the collisions which conserve energy and momentum. Now, keeping the volume fixed, consider now a sequence of systems with different particle numbers and different diameters, such that the number of particles goes to infinity, the diameter of these spheres or balls goes to zero, while n times d squared goes to a constant b, strictly positive. On the other hand, since d goes to zero, which means a fraction of volume occupied by this particle, which is like nd cubed times pi over 6, goes to zero. And this is called the Boltzmann grad limit. Grad is the person, I think, who first introduced this formally. So what Lanford says, take some smooth function f naught xv, which again, a smooth distribution of integral 1 in the six-dimensional space. Now consider, now you are looking at the sequence of systems. As we said, you're changing n, and we are changing the diameter, and then such that basically n times d squared, which is related to one of the mean free pairs, is fixed, while the fraction of volume occupied by the particle goes to zero. And look now at the six-dimensional, look now at this 2n dimensional or 6n dimensional full phase space in where you have a region which corresponds to a macrostate specified by F naught. And then consider as you make the number of particles increase, their volume decrease, that the fraction of particles in a region delta alpha comes closer and closer to this prescribed a priori six-dimensional distribution. And it's a limit, it's in fact, it's a string Boltzmann grad limit, it's in fact equal to it. So in order to make a precise mathematical theorem, you have to take some kind of a limit. Otherwise, you would have to talk about Poincare recurrence times and other things which you want to avoid. So Lamford theorems then says that I'm not sure if I can. Lamford theorems then says, I hope you can see that, the macrostates M sub F corresponding to a given F naught at a microstate in this region gamma F naught will typically evolve via the Hamiltonian dynamics to a microstate X and T such that for all different regions delta alpha, the fraction of particles in delta alpha is given again by some function F, where this function F satisfies the Boltzmann equation. I will not go into describing what's the Boltzmann equation. This is standard textbook thinking the Boltzmann equation. And with the solution of this Boltzmann equation for the initial state F naught. So this is essentially Lamford's theorem. Namely, start out with a microstate in the phase space region gamma F naught, then almost all microstates in that region will typically evolve such that the fraction of the fraction of particles in a given region dx, in a given region delta alpha is given by this one. So this f of x vt is what would be called the empirical distribution, looking at a given system and looking what fraction of particles are in the region delta alpha, the six-dimensional space. And typical with respect to the uniform distribution. So the Boltzmann equation then gives a deterministic evolution from the macro state mf naught to the macro state m of t in the Boltzmann grad limit. Of course, physically, you don't take such a limit, but what it means that it's true in the limit is that it will hold to a very good approximation for a macroscopic, it will hold to a very good approximation for a macroscopic dilute gas. It will accurately describes the time evolution of the empirical distribution of atoms in the one particle space in such an individual system. And of course, one uses the Boltzmann equation indeed in practice for all kinds of things, for airplanes flying and for other dilute gases. Now, the Boltzmann entropy for such a macrostate described by a six-dimensional distribution F is, as just like we defined before, you have to take the log of the region in the full energy shell corresponding to the macrostate MF, And Boltzmann actually did a computation of this for a dilute gas and found that it was given by this formula, namely up to constants, the Boltzmann entropy for macroscopic system of a dilute gas with n particles will be given by minus f of x v log of xv. Now, this equation looks like and sometimes mistakenly confused with the Gibbs-Shannon entropy, which I'll define per particle for a system in a product measure of the form gamma xv. But it's conceptually not at all the same. SBF is the entropy of an individual system with empirical distribution f of xv. You can compute, this is done standard textbook, the actual value maximizes SBF over all different distribution, and you find it's given by the Maxwellian distribution, exponential, here I've put in the mass over there, over KT. And the entropy, in fact, when dilute gas is in equilibrium, is then given by this formula corresponding to this six-dimensional distribution F equilibrium over there. No, the second law now says that for a typical microstate of a dilute gas with initial microstate corresponding to F naught, namely the microstate is that region, and this is not equilibrium, then the macrostate corresponding to the distribution F in time t has to be such that the entropy of this macrostate, F sub t, should be non-decreasing in time. And this is exactly what Boltzmann proved, so-called famous H theorem, that if F satisfies the Boltzmann equation, then the time derivative of this entropy, which is defined as the log of the volume in the phase space. And then as Boltzmann realized, in some respect, they have even generalized the entropy principle here, and that we have been able to define entropy for a gas that's not in a stationary state. Namely, you could have a velocity distribution which is different from a Maxwellian and which evolves in time according to this one. Okay, I think this is the time we're going to stop for questions and for a 10-minute break. Is that all right, Abhishek?
Yeah.
Okay, so let's stop now if you want to have any questions or have a 10-minute break.
Yeah, so I'll, okay, so do you want to take the questions now?
Yes, you can take some questions. I mean, one or two at least.
Okay, so so there, I mean, I think this is one question several people have asked. Why are linear and momentum, angular momentum not conserved? In I think you mentioned that you assumed linear and total moment, angular momentum.
As I said, I'm thinking of my system in a box with a cubical box with specular reflections at the boundary. Therefore, the total momentum is not conserved. If it was conserved, then I should really take it into account and consider a microcanonical ensemble with a specified linear momentum or angular momentum. So just to make things simpler, I've assumed that the total linear momentum, angular momentum, is not a constant of the motion by having the particle in a cubical box rather than a periodic box, or in a cylindrical container. Instead, I have it in a cubical container.
Okay. So another question is, how do you know that gamma M equilibrium is okay, is smaller than gamma E? Okay, I guess it's
Yeah, because gamma E obviously contains regions where the density is very different from the uniform one, or the energy density is very different. Or you could have all the particles moving parallel to each other in one direction. That would still be part of gamma E, because if you fix the total energy. But it's definitely not an equilibrium system.
Okay,
So you know that it's smaller. The remarkable thing is essentially law of large numbers, that the dominant equilibrium state takes up almost all the volume of gamma E.
Is the reason why Boltzmann's definition of entropy works in the form of logarithm simply because the measure of gamma m scales exponentially with the system's degree of freedom?
Yeah, I mean, you want to have something which is extensive, which goes, and therefore you have to take the logarithm. You can give many other reasons. That's a natural one. Yeah, but basically, this is a quantity. If you have two independent systems and you want to compute, let's say, both in equilibrium, if you want to compute their entropy, it should be additive. And if you take the log, that has a property of additivity. If you took a square root or something like this, it would not have the property of additivity.
Right. Okay. So, isn't ergodicity inherently necessary for equal probability of microstates in the microcanonical ensemble?
No, not at all. I mean, as I said, we are assuming that the microcanonical ensemble there has a relationship to physical systems in terms of small phase space volume corresponds to small probability. But in the kind of properties of the system we are interested are those which are given what I call thermodynamic functions, namely functions which are the sums of one particle or two particle things. Not, I could make up functions like takes a product of the velocities of all the particles, or the x component of velocities. That's a perfectly good function, but there's no necessity or no interest why that the time average of that function should be the same as a microcanonical ensemble average. And as I say, really the average, the crucial part is that the average is really not just an average over many different possibilities, that almost all the properties like which correspond to thermodynamic functions, like the number of particles in a certain region of the box or the kinetic energy are typical. I mean, in fact, maybe I should mention that. I mean, when there was an objection to Boltzmann saying that the Maxwellian distribution is really just one of an infinitely many different kind of distributions. What is special about this one? And Boltzmann's answer was that what is true is that for a large system, almost all phase points corresponding to the energy surface will have an empirical distribution of velocities, which is very close to the Maxwellian. So that's a crucial property. It, as I say, and it's not really related to mathematical ergodicity theory. Of course, if you have integrable systems like ideal gases, or we have to worry about how to do it in some cases. I mean, in the Boltzmann grad limit, starting with a distribution which is F naught, which is not the Maxwellian, you will approach the Maxwellian distribution via the Boltzmann equation. On the other hand, if you really started with an ideal gas with point particles, the definition of the macrostates would still be the same. And the equilibrium macrostate would correspond to the one with the Maxwellian velocity distribution. But if you start with a non-Maxwellian velocity distribution, you will never reach that macrostate. So so it's important in this case that you have the collisions. But what's not important is that functions, as I said, like the product of the velocity square of all the particles should have the same time average as ensemble average. I think maybe we should have the break now.
Okay, yeah.
So let's start again, what, in 8 minutes or 10 minutes?
8 minutes. Yeah, maybe in 10 minutes, okay.
Okay, so we'll start at that time. I see.
Okay.
So, Abhishek,
Yeah.
could you see my pointer or not?
Yeah,
You can see the pointer?
can you move it now?
Yeah.
No, actually, we don't see your pointer.
I said, I don't know what I can do to make it visible. I think that would be.
I guess it's.
I guess, I mean, how did it work in terms of visualization?
I mean, it was quite, I mean, like, I think, I mean, we could basically follow like where you were.
So yeah, I don't know how to make the pointer visible.
I think you might have to. Naveen, do you know?
Yes, sir. Is it Keynote, no, sir?
Sorry?
Keynote you're using?
No, this is a PDF file.
PDF file.
This is what's a PDF file, yeah.
Yeah, I think maybe it's better not to. I think because
Okay.
we may
Let's not do anything.
Right, yeah, there might be again be a problem.
Yeah, and I say I'm behind schedule. Do you want me just to stop at, I guess my time would be 11:30, or are you going to tell me when I should stop? I might not get, again, I certainly will not get to the end of the slides.
I mean, like you can, if you want, you can take some more time, but you can stop whenever you feel is a good time.
No, okay. Well, you let me know when also if you think I should stop. Okay.
Yeah.
So, and you can see me while I'm talking.
Yeah, we can see you. I mean, yeah. But yeah.
Okay. I'm going to get myself a cup of coffee, and I'll be back.
Okay.
And be ready. Okay.
So Joel, there was one, one question. Maybe I'll just. So.
Go ahead.
Yeah. So, so where in your arguments or Lanford's does infinite sensitivity of the dynamics to initial conditions enter?
Well, in the actual proof, you use the actual time evolution for hard spheres in their collisions. So it's a proof, actually, I guess I should have mentioned, has been extended by Lanford students to more general repulsive potentials, short-range repulsive potentials. I don't think it's used explicitly, but the properties of collisions of hard spheres do enter. I think the proof would probably not work if you have hard squares. At least I don't think so. But I don't think you sort of you just look at the actual dynamics of the system, and whatever in it, it is true that for hard spheres, you would have sensitive dependence on initial conditions, but I don't think it's used explicitly in any place. So do you think it's time to start?
Yeah, we can start if you're ready.
Yeah. Okay. So tell me when. Tell me when I should start.
Yeah, I think you can start. And yeah.
Okay. Well, okay. Let's continue. I will be maybe skipping some things. Basically, saying that what is true for the Boltzmann equation, which can be derived, say in this Boltzmann grad limit, and is true for dilute gases in general, and it's not even necessary to have hard spheres. You can have more general short-range potentials. Supposing you are given that you have a time evolution of the macroscopic equations, like the heat equation or something like that, so that there is that the macrostate effectively satisfies an autonomous equation. Then you have to have it follows then from the second law, or rather, it follows from the fact that the phase space volume is conserved, that if you start out in a given macrostate, and then if the deterministic law for the macrostate evolution tells you it goes into a new macrostate, then the volume of this new macrostate has to be larger or equal to the volume of the initial macrostate because of the Liouville theorem of conservation of volume. It cannot go to a smaller macrostate. And so this leads to, essentially, if you do have a macroscopic evolution like the heat equation or Navier-Stokes equation, it leads to the fact that this equation has to satisfy the properties that the Boltzmann entropy of the macrostates, which is the log of the phase space volume, cannot decrease. But of course, it's not true backwards in time. If you could reverse the velocities perfectly, you would go indeed back in time. And in Lanford's theorem, of course, you start with some general initial state, a microstate in this region, and you prove the theorem. And in fact, then you can show that indeed you get a time asymmetric evolution, which increases in entropy. But what about in real life? Like if you have events which occur maybe not even many humans, you have a meteor crashing into Jupiter or something like that, which again is definitely an irreversible behavior. Where does this asymmetry in time come about? Since, as we said earlier, that Hamiltonian equations of motion are time symmetric. Reversing all the velocities, you'll get back to it. If you could perfectly reverse all the velocities in a macroscopic system out of equilibrium and keep the system perfectly isolated afterwards, we would have a violation of the second law. So if you started out with a non-uniform density, say all the particles in the left half of a box, and then you let it evolve until it becomes more uniform, but still not, and then you reverse the velocities, it would go back to the initial case. And this was, of course, what was great objections to Boltzmann's derivation, or to Boltzmann's result, that you have a time asymmetric behavior, entropy increasing, while the microscopic laws are reversible. And so, so what Boltzmann said, what is, where is it? So this was one of the main objections to Boltzmann, thing. But where is it? I wanted to find it. Let's see, I don't know where to. Anyway, what Boltzmann said, that is that one must realize that time evolution of a physical system depends not only on the equations of motion, but also depends on initial conditions. And that it's important, crucial thing is that these initial conditions are ones which correspond to low entropy. And so it's a question, what corresponds to appropriate choice of initial time and initial conditions for which one can reasonably make the assumption that you start in a state which is atypical of the energy shell. Because for a typical state, you would be in equilibrium, but you start in it because it's in a low entropy, non-equilibrium state. And then if you think about it, for real systems, one is pushed to consider the very beginning of the universe we live in. In our current understanding, this would correspond to the Big Bang, but quite as whatever it is corresponding, but Boltzmann's response to the objections that while his equation gives a time asymmetric behavior, while the actual microscopic laws, Hamiltonian equations of motion or Schrödinger equation, in fact, give you time symmetric behavior. And Boltzmann's answer was, from the fact that the differential equations of mechanics are left unchanged by reversing the sign of time without changing anything else, Herr Oswald, he was one of the critics of Boltzmann, concludes that the mechanical view of the world cannot explain why natural processes always run preferentially in a definite direction. But such a view appears to me to overlook that mechanical events are determined not only by differential equation, but also by initial conditions. In direct contrast to Herr Oswald, Oswald was a chemist, by the way, a famous chemist. I have called it one of the most brilliant confirmation of the mechanical view of nature, that it provides an extraordinarily good picture of the dissipation of energy, as long as one assumes that the world begins in an initial state satisfying certain conditions. I have called this state an improbable state. What it means really is a state of low entropy. Feynman again, emphasizes, says it's necessary to add to the physical laws the hypothesis that in the past, the universe was more ordered in the technical sense, meaning having a low Boltzmann entropy, than it is today, to make an understanding of irreversibility. And here is a picture by Roger Penrose about the creation of the universe. The creator, he has to find the microstate in which the universe begins. Started, has to find a tiny box, just 1 in 10 to the 1023 of the entire phase space volume, finds a macro in order to create a university with as special a Big Bang as we actually find. In the tiny box in the figure is a macrostate with low Boltzmann entropy. Nota bene, and this already was noted by Boltzmann, it is not necessary to select a particular microstate. Almost all microstates in the low entropy macrostate will behave in a similar way. So you just have to select a macrostate, which is a low entropy state. Now, saying a question which comes up and I was actually asked in a seminar I was giving at one point, somebody was having a glass of tea with sugar, putting a sugar cube in it. Asking, what does the initial state of the universe have to do with the fact that when I put my sugar cube in my tea, it dissolves irreversibly? And the answer is, my answer was nothing directly, but the fact that you, the sugar cube, and the tea are all here is a consequence of the initial low entropy state of the universe. If it started in an equilibrium state, then of course we would not be here because the system would just remain in an equilibrium state. But starting in a non-equilibrium low entropy state, you can have a world which looks like the way it looks now, in which time evolution of macroscopic systems are really irreversible, even though the microscopic dynamics are reversible. Just to here, let me to conclude the classical section. It says, I want to contrast the Boltzmann entropy with the Gibbs-Shannon entropy. I guess it's a Gibbs entropy for equilibrium systems, and you have in Shannon entropy in general information theory, which is an entropy associated not with a particular microscopic system with a well-defined microstate, but rather with a distribution mu or an ensemble density mu, saying if mu indeed is a form that it's uniform over the phase space region gamma m, so by normalization, that it would just be 1 over the volume of gamma m for the microstates being in gamma m and 0 otherwise, then if you computed the entropy, the Gibbs entropy, I guess, but here S mu is here G for Gibbs, then this Gibbs entropy would be the same as the Boltzmann entropy for a distribution which is uniform over a region of the phase space corresponding to a given macrostate. And this, this is essentially the case for the microcanonical ensemble, since, as we said, the whole energy shell is dominated by the macroscopic equilibrium state. And then, so that's a uniform distribution over the energy shell, namely the microcanonical distribution. If you compute its entropy, you'll get exactly the Boltzmann entropy for an equilibrium system. And where it talks that. And then it's also, if you look at the canonical ensemble, you have equivalence of ensembles. So computing the Gibbs entropy for corresponding to the canonical distribution mu, you will again get the same. So that for the equilibrium systems, or for systems with a uniform distribution over the region gamma m, you would have the same entropy. The Boltzmann entropy is the same as the Gibbs entropy for macroscopic system. However, if you consider isolated non-equilibrium system, which evolve in time according to Hamiltonian equation or according to the Liouville equation for the ensemble, then you find that the Gibbs entropy for the probability distribution mu doesn't change in time, and therefore is useless for describing the actual time evolution of the entropy for a macroscopic system. On the other hand, the Boltzmann entropy, which depends on the microstate x at time t through its macrostate, captures the essence of typical macroscopic behavior. In particular, it satisfies the second law. And this is a picture of Boltzmann's headstone on Boltzmann's grave in Vienna, which has, if you can see it, S equals minus K log W. In some summarize, time asymmetric behavior as embodied in the second law of thermodynamics is observed in the visual macroscopic system. It can be understood as arising naturally from time-symmetric microscopic laws. When I'm going to state now the great disparity between microscopic and macroscopic sizes, initial conditions. And I say initial conditions for real life, you have to go back to the initial universe. And that what we observe is typical behavior, not all imaginable ones. You can construct systems even approximately realistically, where you can implement for a short time at least this time reversal and therefore changing, going in the opposite direction. And then again, alternative explanations, such as equating irreversible macroscopic behavior with organic or missing properties, are, I think, in my opinion, misleading. Well, here I just skipped it. I mean, there's Einstein's tribute to Boltzmann. Says on the basis of kinetic theory of gases, Boltzmann had discovered that aside from a constant factor, entropy is equivalent to the logarithm of the probability. Anyway, so again, Einstein is just saying what I was saying there. He recognized the nature of course of event in the sense of thermodynamics are irreversible. Seen from a molecular mechanical point of view, however, all courses of events are reversible. You could reverse the velocities. If one calls a molecular theoretically defined state a microscopically described one, this is what I called capital X, or briefly microstate, then an immensely large number of zero states as we belong to a macroscopic condition. And Z, this is classically would be the volume of the region in the phase space corresponding to a macrostate, is then a measure of the probability of a chosen macrostate. And this, Einstein concludes, this idea appears to be of outstanding importance, also because of the fact that its usefulness is not limited to microscopic description on the basis of mechanics. And in fact, let me go as far as time is up. Let me turn to quantum mechanics. These are very different on the microscopic level from the classical systems, but quite similar to the on the macroscopic level to a classical system. And so the first question is, how do you describe a microstate quantum mechanically? Classically, there is no problem, just specify also positions and velocities. But this is, of course, not possible quantum mechanically. And I say, unfortunately, there's no consensus, but I will take it to be essentially that the microstate of a macroscopic system with energy in a narrow interval to be a wave function psi, which belongs to a shell in the Hilbert space, namely that this Hilbert space region, shell HE, consists of all linear combinations of energy eigenfunction in this range, where delta E is small, but large compared to the spacing between levels. I say this is not perfect because there's this problem of Schrödinger's cut, but for this talk, it will have to do. Instead of a pure state, you could use a density matrix with eigenstates in this energy shell HE, and this would give you the same. So the point is, the next question is what corresponds to a system being in thermal equilibrium? I mean, what is the analogy of a classical microstate X lying in gamma equilibrium? Now, following von Neumann is this von Neumann in his book, chapter 5, rather than the usual thing. You take von Neumann density matrix, entropy. We take the macro observables corresponding to the macrostate M to commute with each other, so that you don't have to worry about non-commutivity. You do some rounding off. And so you can define the macrostate of the system in terms of macro variables which commute with each other. And then you also coarse grain the energy operator. And basically what you do, instead of dividing the energy shell before gamma E into regions corresponding to different macrostates, gamma M, you divide up the Hilbert space to an orthogonal decomposition in terms of Hilbert spaces corresponding to particular macrostate. Namely, each subspace consists of all linear combinations of the joint eigenvectors of the macro observable whose eigenvalues lie in a narrow range. And these subspaces, as they correspond to the different macrostates we had before, and to the orthogonal decomposition of the energy shell in the Hilbert space corresponds to the subdivision into disjoint regions, gamma M of the classical energy shell. And then we say quantum mechanical, the system is in the macrostate M sub mu if its wave function psi is close to the Hilbert's linear subspace of the Hilbert space H mu, in the sense that the projection is close to 1. And I say there's a problem with the Schrödinger's cat. Some wave functions are not close to any particular macro state like Schrödinger's cat. But then one would have to go beyond the Copenhagen interpretation, maybe Bohmian interpretation. But for the present, I would say I would interpret such a psi like the Schrödinger cat, a superposition, as really just giving probabilities of being in either states for macroscopic systems. In sense analogy of the phase space volume, gamma M, and this is done by von Neumann, is the dimension d mu of each macro space, h mu. And then it's again, one can show that for this kind of Hamiltonians we're discussing that there is an equilibrium macrostate such that the dimension of the subspace corresponding to equilibrium is almost the same as the dimension of the whole energy shell. And then the Boltzmann entropy is basically defined as the log of this dimension. And then essentially everything we have said classically can be transferred to quantum mechanically, namely going to larger regions of the phase space corresponds to going to to subspaces of the Hilbert space with a larger dimension. It's very nicely explained in a Griffith's article where it gives the references given to it. So in sense, you again have Boltzmann's argument that an isolated macroscopic system out of equilibrium will go towards equilibrium, similar to that in the classical case. Now, when I say here most psi, before when I said most x, I meant the measure of the set of x's in the microcanonical ensemble or in a region of the microcanonical ensemble. Here, I mean, by most psi, I take a measure on the Hilbert space, H sub E of the shell over there, and put a uniform measure on that. Again, that was discussed by Felix Bloch a lot as an analogy to the microcanonical ensemble. And this is a much more detailed kind of thing than just saying that just giving the density matrix, giving a distribution over all the wave functions. Now, I want to come before stopping just to this point, that unlike classical system, where if you have a subsystem of a system in a given microstate, then the subsystem will itself be in a specified microstate, having positions and velocities for all the particles. Quantum mechanically, you can have a situation where the whole system is described by a wave function, but the subsystems will be described by local density matrices. And these density matrices could be very close to what you would get from having a microcanonical ensemble for the whole system. And we call that in joint work with Shelley Goldstein, David Hughes, and Radi Tomolka, which is given in the references. We call that instead macroscopic thermal equilibrium. We called it microscopic thermal equilibrium. Namely, you take a system, even it could be in a pure state or what, but you look at the density matrices of small subsystems, then these density matrices obtained from the wave function for the whole system, or from some density matrix, which is in an energy, you will get that the subsystem density matrix is very close to the what you would get from the microcanonical ensemble of it. So this is what we call that such a system is a microscopic thermal equilibrium. I guess I don't have time to go into detail, but in fact, what is true is that most wave functions in this energy shell of the Hilbert space have the property that a small subsystem of the large system will have a density matrix obtained by tracing over the large part of the system as if it came from microcanonical ensemble. And then, I say interestingly, computationally, to hold for systems, Hilbert spaces with small dimensions. And this brings up many questions, including the stochastic thermodynamics, which really deals with small nanosystems, not coupled to heat reservoirs. But I say I don't have time to go into that, and I will just leave you now. And I say I'm sure that it will put the slides on the web page, and you can read the references over there. So thank you very much for your attention. So I'm stopping now, Abhishek.
Yeah, thanks a lot for really great talk and for the insights. So I think there are still many questions, but maybe
okay, I can answer a few. I'll try to answer. Are you going to ask some, Abhishek?
Yeah, maybe I'll just ask one or two. can one show that the subsystem's density matrix will converge into a diagonal matrix if the whole system size goes to infinity? I guess.
Well, I think yes. I mean, as we said, is that we expect, just like in the case of classical system, if you start out with a wave function which describes a non-equilibrium macrostate, like having different number of particles on the left half or the right half of the box, then again, by the same argument as before, that you expect typically the system to go to macrostates with having larger phase space volume and eventually to the equilibrium one over there, that quantum mechanically, again, you expect the wave function to evolve in such a way that it will get close to the equilibrium sub-Hilbert space. Yeah, and in the equilibrium superspace, you can compute whatever it is, the density matrix of a subsystem will be the same as what would you compute from the microcanonical ensemble, or for a large system, whatever you would compute from the canonical ensemble. So whatever that gives you for the subsystem. And I guess if it interacts weakly as a subsystem, then you get essentially a canonical distribution for the subsystem. But even if it interacts strongly, you have a well-defined prescription of how to get the density matrix of a subsystem in equilibrium by doing trace over the microcanonical ensemble. Once you have that wave function has gotten close to the equilibrium subspace.
Okay, right, yeah.
So Joel, I mean, I had one question. I mean, so like from what you said, it looked like there's no classical version of might, right?
At least we don't have any good idea how to define that.
But on the other hand, like
it's a very special property of quantum systems, related certainly to entanglement and things like that, that you can specify your full system by a given wave function and still have that subsystems have density matrices, which are close to what you would get from a canonical distribution.
right.
We don't have any real analog to that classically.
Okay. Okay, maybe there are two last questions. The entire universe as a phase region such that the probability distribution of thermal energy arises from quantum fluctuations inside the microstates and acts as a source for the background temperature of the universe.
I don't know. That's really, I guess, difficult questions to this cosmology. I mean, I was focusing myself, I say, on physically isolated macroscopic systems, but not the whole universe. I mean, people certainly have considered that, and but I don't have any answer to that, which I can give at the moment.
Okay, and then this question is, could on the relevance of the second law for classically gravitationally interacting systems.
Well, I think the basic thing is still true. So, of course, since the Hamiltonians are very different, it's no longer true that entropies are sort of additive. Or if you bring two suns together, they will merge. If they merge with it gravitationally, I mean, or you just bring them together, they have the interactions between them. Gravitational interactions are long range, but that you don't have an additive form of the entropy. However, the fact is that if you take the natural dynamics of the time evolution with gravitation, you should still have a good version of the second law for applying to that. Of people have in particular, of course, also describing as entropy of black holes, the second law over there. In fact, there was a talk last week, seminar I run by Juan Maldacena discussing these entropies. You can find that talk on my webpage, recorded. But I think it's really a big subject, and I not able to go into it at this point.
Okay, so I think maybe it's there are still many questions, but I think it's a good time maybe to stop.
People can certainly send me email with questions. I'll be very happy to respond if you send me an email.
Okay, so and all the slides of this entire lecture will be put on our website, and also the video will be there very soon, so people can have a look at those. And so thanks everyone, and thanks a lot, Joel, for this really a great talk, and for explaining why statistical mechanics works. I hope there will be textbooks where this is made clear. Like we discussed, there are a few textbooks which do make this point of typicality, but yeah, so thanks again.
Okay, thank you. Bye-bye.
Bye.
Good to see you. No, I can see you. I couldn't see you at all during the talk. I guess, thank you, everybody. I'm sorry that we had so much trouble, but I'm glad we started at least early enough that I hope the talk itself was okay.
Right, yeah, I think you can see some people now. Yeah, and yeah, I think next time we'll figure out how to, so that you can see people and you yourself.
Yeah, well, thank you very much. We'll be in touch. Bye-bye, everybody. Thank you.
Bye. Oh,
yeah, Professor, we'll switch off the stream. Shantaraj, yeah.